Thanks for downloading a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online. Now stay tuned for your 3CR podcast.
Hello and welcome to another episode of Lost in Science, 30 minutes, wall-to-wall science. We're so glad you're here with us. My name's Lyndon and I'm joined in the studio today by Claire. G'day Claire, how are you?
Hello Lyndon, I'm so well. Better after hearing your lovely voice.
And you. It's been a while, I reckon, since we've had an all-ladies show.
Yeah, it has been, yeah. The Lyndon and Claire show, watch out.
No disrespect to the boys, but it's really nice to see you.
It's nice to see you too. And what a show we have. I mean, we've both brought stories today. Mm-hmm. I'm looking forward to hearing your story.
Well, I hope you are. Look, this is a story that might not tickle everyone, but the term tipping points has been in the news a bit lately. I'm not sure if you saw the news about one of the many climate tipping points that you hear around, the Gulf Stream slowing down, or a tipping point from which there will be no comeback for the coral reef. But the tipping point that I wanted to talk about today is a tipping point that happens in maths.
Oh.
It's
related to climate?
No, not related to climate at all. I mean, we can talk about climate if you want, but this study that came out a couple of months ago was actually done by a group of psychologists in the US, and the study was trying to see if you could predict the aha moment that mathematicians have. And this is such an interesting concept, combining this idea of how mathematicians do their work on blackboards, trying to understand and answer, quite complex mathematical problems, and whether you can apply a model to predict when that eureka moment is going to occur. And this study was published in PNAS just a couple of months ago, and I thought it deserves some attention. So that's what I'm bringing to the table today.
I can't wait to hear more about that.
What about you?
I'm tipping over. I'm tipping over into that story. Well, this week I'm going to bring you some really weird and wonderful, even weirder and more wonderful biology from the ant world. It is some really freaky stuff going on with ants.
I mean, it's always freaky with ants, isn't it?
Oh my gosh, it is always freaky with ants, but this is the freakiest of the freak, Lyndon. It's so crazy. So researchers have just published in Nature that showing that there's an ant species that can actually give birth to two different species.
What?
Yes.
You look scared. You look like, I'm not here. I don't want it. I don't want to live in a world where this is happening.
Yeah. It's just one of those things where you think you know about something, but actually you don't. You don't know about something. You think there's a rule for something, but actually rules are just meant to be broken.
By ants.
So, usually by ants. Yeah. Yep. So we're going to take a look at that fascinating research today.
Fascinating and terrifying. Let's do it. Welcome back. You're listening to Lost in Science, and I'm wondering what you think of when you think of Archimedes.
Oh, definitely a bath.
A bath, yeah.
And eureka!
Yes. Eureka, when he realised that his body weight was just the weight of the water that he was displacing equaled the his weight. Is that,
Yeah.
is that the Archimedes principle? Oh my gosh.
His volume?
His volume. That's right. His volume. Yeah, that's right. The Archimedes principle. Him yelling, "Eureka, I figured it out," running down the street naked, super excited that he'd had this brainwave, right? He'd had this flash of insight, like a flash of lightning, hit him like a bolt of lightning, and he suddenly understood what was going on, right?
Yeah, yeah.
These kinds of eureka moments that happen in all sorts of fields are similar, some psychologists think, to tipping points, or they're called critical transitions, right? Critical transitions that can happen in all sorts of places. They can happen in ecology, in physics, in climate change, as I said in the intro, you know, where you've got that abrupt shift from one state to another state. Mental health is the same. It's kind of the world's going along in one sort of way, and then something happens, something's destabilized, and it resets at a different level, right?
Right.
This kind of shift in some contexts is considered to be bad, right? A tipping point where you've got a massive loss of an ecosystem or species decline, or when you see a kind of catalyst sort of occurring in physics or chemistry, but can also be seen, as Archimedes showed, as a positive thing, right? And this is
you're normally not going back from a tipping point, though, are you? It's
No.
like it's only going forward. It's a change of state, and there's no going back.
No, it's a step change, right? It's a shift from one state into another state. And some American researchers were psychologists, right? They're psychological researchers, were really interested in exploring this concept of a tipping point in the framing of mathematicians. I'm talking like pure mathematicians here whose equipment is a blackboard, not even a whiteboard, a blackboard. And that's what their job is, to work at a blackboard every day to solve theoretical mathematical problems, right?
So I'm just imagining like Goodwill Hunting, like that sort of thing, like being on the board. Okay, wow,
that's what I'm imagining as well. Well, I'm not just imagining. Saw it in the paper. So this is what they did. This is actually what they did. I got to use the exact terminology that they had in the paper. So these guys wanted to see if they could develop a model to predict the tipping point or the aha moment or the eureka moment of mathematicians working on a difficult problem. And they did that by studying them in the wild, right? They stole a technique from ecology where you like film species in the wild and see what their behavior's like. These researchers filmed 6 mathematicians in the wild, aka in a seminar room or in their offices, trying to solve mathematical problems. The problems came from the William Lowell Putnam Mathematical Competition, which is the most prestigious mathematical competition in the US, right? It happens every December, and it's 12 questions, I think, over 6 hours, right? This competition. And to give you an indication of how difficult they are, it's 120 points up for grabs in this competition, and the median score is 0 or 1. Most years. So it's like the best maths competition in the US and Canada. PhD level mathematicians come and do this competition, and it's really, really, really hard. So these 6 mathematicians who volunteered to be a part of this study were trying to answer questions from this competition.
I mean, by the sounds of it, they were more likely than not going to get an aha moment in this competition.
That's true. So the researchers watched like 4 or 5 hours of footage of these 6 mathematicians trying to solve these different problems, and they monitored every time there was a transition movement, right? So the mathematicians are writing numbers on the boards, they're drawing shapes on the boards, they're connecting dots, they're connecting lines, they're drawing lines, and every time the mathematician moved from one point to the other point, they kind of noted that down as a separate movement. There's over 4,500 movements, right, that these researchers documented to try to identify a pattern. And they note what they found was that there was a bunch of kind of predictability that would occur where the mathematician would connect, oh yes, this theory or this equation with this diagram, and they'd move between, quite common elements on their board. But in the couple of minutes before they had their aha moment, so there were 27 aha moments identified in this footage, most of them verbal as well, accompanied by, oh, I get it, or, oh, I see, or genuinely someone going, aha, like they documented that. In the 2 minutes before that occurred, there was increased unpredictability, right? So you can imagine that a mathematician, she's looking at, I don't know, a matrix she's drawn and then a triangle that she's drawn and a line or a graph or something, and she's going from A to B to C to A to B to C. But over in the bottom right of her blackboard, she's got another theorem or another shape or something, and she hadn't connected those two, right? So that hadn't happened. But then in the couple of minutes before, she starts looking between those two, and there's like the unpredictability increases, and she's starting to connect things that she hadn't connected before. And then comes the audible aha, and then there's increased unpredictability for a minute or so afterwards, and then things kind of return to baseline. And this, the researchers found this across the 6 mathematicians, across the different types of problems that they were solving, and it just seems so like meta, perhaps, to apply a mathematical equation to try to figure out how mathematicians solve equations. But the researchers suggest that this is also quite an exciting way to think about how creativity works more generally. Like not just creativity in science, to think that you've got to connect disconnected things to find newness and to find that kind of spark. But also to see if there's a way that by not only predicting when something like that's going to happen, you could almost predict what it's going to be as well. Because you're like, well, by definition, it was connecting two things that you hadn't previously connected by your behaviour. Now you're connecting something that you hadn't connected before. So possibly in some contexts and in some structures where you've only got a certain number of things on a board or variables in some kind of setup, by seeing the ones that hadn't been connected, maybe that can allow you to predict what that breakthrough is going to be, perhaps.
Yeah, and I mean, it sounds like it's a great reason to have a blackboard in your office.
Yeah. The study was at pains to say that blackboards are, the real tools of the trade of mathematicians. Whiteboards, digital options, not the go. It's got to be a blackboard. And they even mentioned a study that says there's mathematicians who hoard a particular type of chalk because that's the chalk that, I don't know, works the
chalk
best.
Chalk of choice.
Chalk of choice, exactly. The researchers also looked at, they kind of hypothesized why this increase of unpredictability could be a precursor to the aha moment. One suggestion is that it's kind of done deliberately. If you are a PhD level mathematician, then you've been taught how to work through very difficult problems, which is to look at things that you hadn't looked at before, to take that step back and try to connect previously unconnected ideas. Or another suggestion was that they were getting increasingly frustrated, and so they were trying anything and everything to try to find a solution to a particular problem, and that means like stepping away and thinking outside the box.
And could the mathematicians have any sort of did they have any of their own reflections on that?
That's a great question. It wasn't a part of the study design, in fact, and there wasn't any component of the research that was about brain monitoring. So that's something that the psychological researchers suggested for future study, to see if there was an increased element of randomness in brain activity as well as increased randomness in outward activity too. It does strike a bit of a strange vibe to think that the mathematicians were really the subjects, right, without being able to voice their own experiences of the process. But maybe having that separation was helpful for what the psychologists were looking for. It does make you, I don't know whether it makes you feel less inspired by Archimedes' eureka moment, and you think about, like in murder mystery novels where the person's ruminating on trying to solve the problem and then the answer just like hits them, whether you think, oh, okay, did it hit you, or were you behaving increasingly randomly for the couple of minutes before it hit you? I'm not sure whether that's ruining the romance of research a little bit, but it's certainly making me think that if I'm behaving in a different way, maybe it's not that I'm super tired, it's that I'm just about to have a breakthrough.
Breakthrough or breakdown?
What are you onto? Anything of interest to the scientific community?
Together, you and I are going to make the greatest single contribution to science since the creation of fire.
It's a big scientific experiment. What do I know?
Across Australia on the Community Radio Network, you're listening to Lost in Science.
You are listening to Lost in Science, and Lyndon, diversity in the animal kingdom. I mean, it really is the spice of life.
You won't get any disagreement from me there.
And, there are some commonly held rules, though, in the animal kingdom that we understand about animals. And one of them seems pretty foundational. And that's when an animal has an offspring, both the mother and the parents and the offspring, they'll belong to the same species. Humans have human babies, cane toads have baby cane toads. And apart from your mules or your ligers, which are a hybridization of a cross between lions and tigers, apart from them, that don't actually, those animals don't reproduce in their own right, that's pretty foundational about how things go in biology.
Yep.
Animals beget other animals. Oh, sorry, animals beget the same species of animals.
Yes, yep. I'm thinking about the channel-billed cuckoo here. I'm being a bit of a jerk, thinking about cuckoos that would leave,
sure.
There's insects that do that as well, and birds that would, leave their offspring for others to raise, but that's not the same. That's not what you're talking about.
That's not what I'm talking about.
No.
And because, when they were making this rule up, they obviously forgot to tell one particular animal.
Who's the they in that sentence?
They. Well, the biologists. Mm-hmm. Forgot to tell the Mediterranean harvester ant species, Mesa ibericus. Because this little ant, it is turning this rule right on its head, or antennae, whatever you like. So, Lyndon, this paper was published in early September in Nature, and it's entitled "One Mother for Two Species via Obligate Cross-Species Cloning in Ants."
Obligate,
yeah.
That's the word that tripped me up there, as in...
Obligate.
Is obligation? Does that have a technical term?
Yeah. Like it has to happen.
It has to happen.
Yeah,
How?
it has to happen.
What does that mean?
Oh
One
my
mother,
gosh,
two
yeah.
species. Unpack this for me.
I know. I mean, that's why we're here. And so the researchers show that this little ant, this Mesa ibericus, so it can and does produce offspring, not only of her own species, so the queen's not only producing her own species, but also of a different species. And this isn't a hybrid. This is offspring of a different species which are capable of reproducing, which they do.
All right. There's so much I don't understand about this. First question. How do ants make babies?
Ants, queen ants, have eggs, and those eggs are fertilized by, normally, I think they're male drones that have sperm that fertilize those eggs, and then those eggs hatch.
Okay.
Yeah. But But let me give you a bit of an overview of the structure of the ant colony, because ants they've all got very specific roles in the colony. So in harvester ant societies, you've got like I said, the female queen who lays the eggs and the babies, and the males who provide the sperm. Then you've got sterile female workers, and they pretty much take care of everything. They build the nest, they do childcare, and interestingly, they make something called ant bread, which, if you'd like the recipe, is crushed up seeds mixed with ant saliva.
Oh, paleo. Sounds good.
Paleo, exactly. Yeah, one of the maybe a weeknight wonder. So when researchers were studying these ants, they noticed something very abnormal. All of the workers, or the ant bread makers in the colony, they were first-generation hybrids, which means they were all the result of mating one species of ant with another one. So think like a mule, like a horse with a donkey.
Yeah.
So that's what these workers were. And they were all crosses of the species Ebericus, Mesa Ebericus, and then another harvester ant species which was called Mesostructor. Yeah. Now, the hybridization itself, like as we've talked about, this isn't weird. It happens in the ant world a lot. Queens mate with a male from a different species, and they create hybrids that might be a bit stronger. And because they're workers, it doesn't matter if they're sterile. So that happens. That can happen. But then the researchers noticed something even stranger. So there were the Mesa Ebericus ant colonies. These ant colonies were nowhere near the other species of ant, the Mesostructor ant colonies. So the two colonies did not meet. Yet there were all these hybrid ants running around. So that would suggest that the queen has gone out and found a male to fertilize her eggs somewhere else. But there weren't any of those colonies anywhere else. So they're like, what is going on? So the researchers began DNA testing the Mesa Ebericus colonies in the wild and in the lab, and they found that that there were actually a number of these other species, these Mesostructor drones. They were living in the colony of Ebericus amongst the hybrids. And so they were like, well, where are these drones coming from? Are they coming from another colony? What was going on? So then what they did is they tested all the mitochondrial DNA of all the drones, of all the hybrids, and of the queen. And you might know that with mitochondrial DNA, as opposed to the DNA that you find in the nucleus of the cell, the mitochondrial DNA comes straight from your mother. So your mitochondrial DNA, Lyndon, is from your mother, which is from her mother, which is from her mother, and so on, so forth, back. Generations and generations. It's the same with ants. So when they tested the mitochondrial DNA of these this other species of ants, these structural ants living in the Ebericus colony, they found that they had Ebericus DNA from the mother.
So the mitochondrial DNA was Ebericus, but their nucleus, like their cell DNA, was the other one.
Yeah, Structor.
Structor.
Yeah, so for all intents and purposes, they were a different species, but the scientists realized that they had obviously had a mother who was from another species. It's just crazy.
Oh my god! So did the
yeah. So from this point, the scientists are like, "What? What is going on here?" And hypothesized that, okay, well, maybe Ebericus was in fact laying two species of eggs. They were laying Ebericus eggs, as you would expect in nature, which is most often the case. But then they were also laying these Structor eggs as well. And And when they tested the eggs, they found that nearly 10% of these Ebericus eggs were actually
Structor eggs.
Yeah.
Really?
Yeah, and what they found were these eggs were clones, and they were growing up into these mesostructor drone ants, and then the queen was using those drones as sperm donors to then create the hybrids, which are the workers, which are the ones that.
It all feels a bit Game of Thrones now.
Bread.
Okay, so
So just as a thought experiment, and this might be helpful because there's a lot of names here. So, Ebericus and Structor, they diverged around 5 million years ago. Mm-hmm. So they're not that related, but it's around the same time that humans and chimps diverged, and evolved separately. So if we extend on this thought experiment, this ant strategy would be like humans having chimpanzee babies, which they then use as a source of sperm to give birth to a human-chimp hybrid that makes us bread. It's weird. It's really weird.
Wow. Did the researchers talk about, like, why? Did they hypothesize any strategies that the Queen was using here? Was it a fluke? Did they find it in lots of colonies?
Yeah, well, apparently it's very consistent across the species. Mm-hmm. This one species. It's the first time this strategy's ever been documented, where one species needs to produce offspring belonging to another species to then be able to continue on its own species. So they've actually got a new word for it. It's called xenoparity, which translates as foreign birth. So these ants are xenoparis, I think, how you would describe them. But that's the new term. And to answer your question, it feels very science fiction-y. It feels a bit of Game of Thrones-y, but it does make sense for them. So if they can store sperm and produce clone drones that they need whenever they need, they're not relying on another colony being anywhere near them to have to produce these drones to then get the sperm that they need to produce the hybrids. So it's pretty much like... It's just like, oh, well, we may as well make them instead of having to be near a colony with this other species. Yet developed a way.
Another woman just saying, oh, righto, I'll just do it on myself then, will I?
Just do it on myself. Oh, I guess I'll just make it then, just make my partner, just give birth. Oh, it's like, yeah. Anyway, so it's a totally weird, totally crazy new life strategy that the researchers have stumbled upon with these ants. And, look, I just hope that the mesostructal clone drones are being welcomed into the new family.
God, that's so crazy. Why did they need the structor? Why can't they just get on with their Ibericus genes?
I think the structor the hybridization must provide some sort of evolutionary advantage. They must be better drone work. No, not drone. They must be better workers when they're hybridized.
Okay.
But it's how much better can you be that you have to have two different species as part of your life cycle?
And I still don't understand where the original sperm came from.
Well, so I tried to get into it, and I think so. So ants have the capability to store sperm for a really long time in these like sperm sacs, and they just keep it there.
The Queens do,
the Queens do.
Ah.
So the actual paper talked about the sperm sacs having 2 different types of sperm in them, that she could just draw them whenever she needed.
That's amazing.
But I don't know how, like, would she have had to be in a colony to get that sperm originally? Like, surely.
There's definitely some, like, stealth spy work going on here. Those ants, they just... I wonder if this is just the first of many. Like, I wonder if they'll find this across other ant species, other insect species. I don't know.
Oh, so weird. So weird.
Well, I'm terrified. Thanks for that.
And that's it for another episode of Lost in Science. Lost in Science is recorded for 3CR in Melbourne on the lands of the Wurundjeri people of the Kulin Nation, and it airs across Australia on the Community Radio Network with the support of the Community Broadcasting Foundation. We would love you to get in touch with us. You can email us at lostinsci@gmail.com, or you can find us on Facebook, we're Lost in Science on 3CR, or on Twitter, where we're at Lost in Science 1. You can find us on your favourite podcast app, where if you get the chance, please give us a good rating and review, as that will raise us up in the search rankings so other people can find the science. Or you can listen to us however you listen to us now, where at the same time every week, Claire, Stu and Chris get
Lost in Science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.